Yeah. All right, so today we are gonna close the vertical kinetics part. So we are left out with like a little something with the impulse and momentum. So let's finish it up. It's gonna take like 30 minutes or something. So we have been talking about, this is the main equation. Here. This is going to be angular impulse and momentum. Right, as you guys know, our main equation of impulse and momentum is mv1 plus the integration of the force dt from t1 to t2 equal to mv2. The body has a momentum, mv1 was impacted by a force. The force has impulse. If you sum the initial momentum with the impulse of on the body, you are gonna get the momentum. And that's what we said. We have a body is moving and has an initial momentum, 10. And then a force impacted this body. This force has a value. This body got more momentum, mv2. Or a body has momentum this way, force applied in the other way, got less momentum in a different direction or something. That's why we need to put vectors here. Force has a vector and V2 has a vector. So definitely the force in a different direction from the initial momentum, the final momentum is gonna decrease, okay? All right, so this is the main equation, but what if we need to talk about not linear momentum? We want to talk about what we are talking about, that you have a body here, something like this, moving on a straight line, and has an initial momentum mv1, and a force is going to apply here for a specific amount of time. This body is going to be here with different momentum mv2. But what if the body is moving on a circular path? Okay, so let's talk about this. So let's say I have my axes like this. This is x, this is y, this is z, right? And my path that the body's moving on is not linear, is something like this. Maybe let's say something general like this, right? And my particle is, let's say something here, okay? This is the particle. Right now, we are not talking about velocity. Like if you guys remember when we, in chapter 13, if a body is moving in a basket, we put the v and the v is tangent. Right now, we are talking about different quantity. It's similar to the velocity, but the mass is multiplied by the velocity, it's the momentum. So we always, and it's always tangential, something like this. So you have mv. This is the momentum of the particle, okay? So the angular momentum is a quantity. Let's actually write it here. Number one, angular momentum. So the angular momentum is the moment of the particle linear momentum. Do you guys know the moment? What is the difference between the force and the moment? The force is something applying on this body this way. That's a force, okay? But if you want to get the moment of this force about anything, you need to multiply by the arm of the force. Like for example, if I'm holding this from here and putting my force this way, so this is a force. It's a quantity different from the moment. If I want to find the moment about this point, I need to multiply this force by the arm of this force. So if this force is 10 and the arm is 5, you multiply 10 by 5, you get the moment 50 ton meter or 50 kilonewton meter. That's the moment. The moment of any quantity that you multiply by an arm. So if you have a force, you multiply the force by its arm. If you have a momentum, you multiply the momentum by its arm. Same thing here. If you want to find the moment of the momentum, okay, we need to make difference. Momentum is different from a moment. Momentum is a mass by velocity. Moment is a force multiplied by arm. I want to find out what is the moment of the linear momentum. So to find this, and when you say moment, it should be about a specific point. Okay? When we say force, it doesn't matter. We need to know the point of application of the force. But if we want to get moment, we need to find what is the moment about. Because if I have a force here, the moment about this point is different about the moment in this point is different about as soon as the arm of the moment is getting increased, the arm of the force is getting increased, the moment is getting increased. Okay, so I want to find out what is the moment of the linear momentum about point O. Okay, so the thing is, I have the momentum is applying here, so I need to find out the position of the particle. So the position of the particle is, for example, I have R vector. Okay, so the angular momentum, we call it HO. So HO is equal to the R vector multiplied by, and this is vector like cross product, mv. And actually, it's kind of similar to the moment. Like, let's say that you have an arm like this, and there is a mass, and this is attached to something like this, and there is a force is applying this way, perpendicular to this arm, and this arm has a distance d. If you want to find the moment of the force F about this point, this is like a 3D. So what is the value of the moment? It's going to be the value of the force multiplied by the distance. Okay, so this is a scalar quantity. We got the magnitude of the moment. Do you guys know what is the direction of this moment?
Right hand.
Exactly. So this force is going this way, so it's going up. So if we are saying F is in X direction, and this is Y direction, so it's gonna be going up. So this is gonna be in the K hat direction. Okay. So same thing is the moment. Like if you want to find the moment, sum of the moment is force multiplied by displacement. So it's the R vector crossed by the force vector. Okay? Just 1 second. So here's the, for example, let's say my R vector is this way and my force vector is this way. So you multiply R by F is going to give you the moment vector this way. Yes?
I was gonna ask you, when we do cross product, we get another vector, right? So
Yeah.
we don't need to do the right hand rule, right? Doesn't just the cross product itself give us the resultant?
It gives you the resultant, but sometimes like this R is not in the X and Y direction. It's not I and like it's not I or J. It's sometimes you have a vector that has I, J, and K, and you need to do cross product. So you either like use the right hand rule if it's a symbol, but if it's complicated, you need to do the cross product exactly. I'm gonna show you how to do cross product for a vector that has 3 components. Okay, so this is actually vector component, has a vector. But if you want to get the scalar quantity of this, HO, you need to find out the direction of MV and multiply D, the distance, the perpendicular distance, by the MV. This is the values. For example, here, R is not perpendicular to the MV. So what I need to do, I need to find the perpendicular distance between MV and the point O, and this is what we call D. Once you find this perpendicular distance and multiply by MV, you will get the quantity of HO, but you don't get the direction. Direction you need to do across product. But actually, if I want to do it, I know that R is going this way, going down, and MV is going this way. So I make my hand like this from R to MV, so the direction is out of the plane going this way. Alright, so let's see what if the R has 3 components, one in the X, Y, and Z direction. Because if you know, for example, it's going to be easy if you have R is in the X direction and MV is in the Y direction, it's going to be easy. The momentum is going to be in the K direction. So if I want to do a cross product, if you guys remember, HO is going to be, we are going to use the formula for this, HO vector. It's the determinant of, we're going to have I hat here, j hat, k hat. And you will put the components of r vector, rx, ry, rz, and then you will have mvx, mvy, mvz. And then you will find what is the determinant, is this determinant is. Do you guys know how to get the determinant? So it's gonna be I, all these components, ry multiplied by vz and minus mvy multiplied by rz in the I hat direction, minus rx, mvz, rz, mvx in the j hat direction. Then rx and vy, so this is how you do it generally, okay? So in the exam, if I give you an R vector that has three components, I, j, k, same thing with mv, and I ask you to find the value of the momentum, you need to find the value of this determinant, okay? All right, so this is as a general rule. This one is very, very important. The angular momentum is r vector multiplied by the mv vector, or it's the moment of the linear momentum. Okay, so right now I want to find out a relationship between the moment and angular momentum. Between, let's write the moment of forces, which is the sum of the moment of the forces about point O and the momentum HO. I want to find the relationship between these two quantities. How can I find this? Okay, let's get back to the basics. The moment about any point O is a vector product, not a scalar product, is equal to the R vector multiplied by sum of the forces on this point. So for example, if I have my x, y, z, this is x, this is y, this is z, and I have, for example, let's say, let's do something like this one that we have here. This is a bat, and my body is here, and this body has multiple forces. It has a force, has multiple forces, like a force this way, a force this way, a force this way, and the sum of all these forces, once you get the resultant, maybe something like this, sum of the forces F. Okay, this is the resultant. The moment of this force, you need to find the perpendicular distance from point O to this force F, and this should be perpendicular. Okay, and this should be D. Once you multiply D by sum of F, you will get the moment of these forces about point O. Or we get the R, the position, R from here to here, and multiplied by the vector of the forces. This is the general rule. But I want you to remember with me, what is the force from the Newton's second law? You guys remember? Mass multiplied by acceleration, right? So we can write this way. It's R vector multiplied by the sum of the masses multiplied by A, and A actually is the time rate of change of the velocity, so I can write it at V dot, right? Let's take the derivative of this moment. Or not the derivative, let's do something else before. So this is the moment, okay? So how about HO? HO vector, we just wrote it up there. Where? Here, okay? It's the R vector, okay, multiplied by cross product MV vector, okay? There's kind of a little bit similarity here. Like this is kind of similar to this. What is the only difference that we have here? Between the moment and the angular momentum.
Acceleration.
Here, this is v dot acceleration, here is this velocity. So let's find out how do we get from here to here. Well, it sounds like somebody get the derivative of this function and tweak it and got this one. So let's find the derivative the time rate of a change of angular momentum. And I don't want to write here so that you guys can see. So I'm gonna continue here. Is it fine?
Yeah.
Okay. So let's find the time rate of a change of the angular momentum. Okay. So I want to find the time rate of a change d dt of the r vector multiplied cross product by the mv vector. Do you guys know how we can get the derivative of these two quantities? Do you guys remember when I have x multiplied by y and I want to get the derivative of xy? So what should I do? I get the derivative of the first, I multiply by the second, plus the derivative of the second multiplied by the first. So this is going to be, what is the derivative of r with respect to t? It's going to be r dot, right? The velocity. And then I will multiply cross product by mv, and actually v is r dot, right? So I can write this as r dot plus the second r vector multiplied by the derivative of mv, so it's gonna be mv dot. You guys tell me, if I multiply r dot vector by mr dot vector, what is the value of this?
0.
0. Why?
Because it's in the same direction.
In the same direction. The theta between them is 0, so sine theta is gonna be 0. So this quantity is 0. So you lift out with r vector multiplied by m v dot. So let's look at this. What is that and what is that? It's the same quantity. So we came up with that the moment of forces about point O is equal to the time rate of a change of the angular momentum of these forces. That's what we came up with right now. So the sum of the forces, the sum of the moment of forces about point O is equal to the time rate of a change of the angular momentum, right? Let's do some integration and stuff like this. So I'm gonna get the dt here. So this is gonna be the sum of the moment about point O. dt is equal to d ho vector. I'm gonna do integration to both sides here. And since I have dt here, so this is gonna be from t1 to t2. I'm gonna do integration here, and I have only ho. So this is gonna be from ho1 to ho2. Once you do this integration, all right, so what if I integrate this? What I'm gonna end up with here? dh, I'm gonna integrate dh. What is gonna be? dx is gonna be x, right? Because we have 1 here. So this is gonna be ho. So I have ho from h1 to h2, right? So this is gonna be ho2 minus ho1. The final momentum minus the initial momentum. That's what's going to be equal to. So we can say that, actually all these are vectors. We can say that the initial momentum plus the integration of the angular impulse from T1 to T2 is equal to the final momentum. This equation is similar to this equation, but this one was a linear momentum, and this was linear impulse, and this was a linear momentum. So this new equation is angular momentum plus angular impulse is equal to the final angular momentum. So let's put them in equation. HO actually is the r vector multiplied by mv1, and this is actually r1. Okay, like my particle was here, has r1, and came here, has r2, and here it has mv1, and here has mv2. All right, plus the integration from T1 to T2 of the moment, sum of the moment MO, with the sum because we have lots of forces, dt is equal to R2 multiplied cross product by V2 vector. That's a really important equation, the second important equation in this chapter. What is the difference between this and this? This is angular, this is linear. So everything here, angular momentum, angular impulse, angular momentum. Linear momentum, linear impulse, linear momentum. That's the only difference that we have here. Does anybody have any question how we drive this? Well, I'm trying in this class, and actually that consumes lots of time, to drive everything with you so that you know where this is coming from. However, we should, like, sometimes, like, I ask you to go and find out by yourself, but I'm trying to do it with you so that you can understand it. But if you have any problem with the derivation, just come and tell me, okay, I don't understand, how did you get this? How did you get that? I'm gonna tell you, okay? All right, so let's solve an example and see how the application work with angular momentum. The example that we have here, alright, says an 80-pound crate is moving around a frictionless assembly. So you have like an assembly here, like a system of pulleys, and somehow you have a cord or an arm, let's say an arm, something like this, and there is a crate has a weight of 80 pounds, and this arm can shrink, like the length of this arm can decrease, and it came to, this is position 1, and this arm at some point was rotating and came here with different lengths, and we have the same body here, okay? So it's moving this way. And this length of the arm was 2 feet, and the length here, let's say this is position 2, is 1 feet. You know that you have like a hydraulic arm, and this hydraulic arm is getting shrink, and in the same time it's rotating. Okay? So let's see what's given here. And that's a top view, not a side view. So everything happened in this plane, not like this. It's like this. That's very, very important. Why it's important? Why when I say that's a top view is different from a side view? Like you have an arm, and this arm is holding a crate, like this, is different like this.
Oh, because one of them is X and Y, and the other one has a Z component?
And how this is gonna make difference?
Um,
What?
the weight?
The weight, right? Because here, the potential energy is 0. There's nothing in the potential energy is changing, right? MGH is the same. But if it's this way, this body, once it's here, it has more potential energy. Okay? It's here less potential energy until it comes to 0. But if it's in the same plane, so the weight doesn't exert any forces here. It's all in the same thing. The weight potential energy here is the weight potential energy. It doesn't make any difference. So this one is a top view. All right, so it says here that the crate is moving around a frictionless assembly line at position 1. The crate is moving with V1 0.5 feet per second, and V1 is something like this. V1 0.5 feet per second. In a straight path, so that's a straight, okay? Just after an arm begins to pulling the crate from R1 at 2 feet to, with a constant radial velocity, VR 0.4 feet per second. Okay, so the arm started here at first, okay? And then, once it has the velocity, this arm is start moving, and in the same time it's moving radially, this arm is shrinking, and it's saying that the VR is equal to 0.4 feet per second. What does it mean? That this arm is going this way, and this way is shortening with this rate, 0.4 feet per second. Let me ask you, is this velocity positive or negative? From 2 feet to 1 feet. Is R increasing or decreasing? It's decreasing. It's negative, right? Because it's decreasing. So make sure when you put the equations, this should be negative. Okay. So what is so number one, what is he's asking for? What is the velocity vector? In R and theta components of the motor at position 2. So he's asking about the velocity vector. Okay, keep attention to that. So here you are gonna have a velocity this way, v theta, and velocity this way, vr. Okay, because this arm has two components. This arm is shortening, and at the same time, it's moving this way. So we need to find these two components. And it's an r theta problem because that's what I'm asking for, r and theta, right? So this number one. Number two, how much work does the arm do? How much work does the arm do? Okay, this arm is pushing this crate this way. So there is a force that this arm is exerting to make this body move from 2 feet to 1 feet. We need to find this arm force. How much is it? Okay, we're gonna do that. Number three, how long does the crate take to get from position 1 to position 2? So it's asking about the time. How long from position 1 to position 2? Let's solve this. The first thing, we need to put this velocity in vectors. Okay, so let's find the initial velocity at 1. At 1, this body was still like a steady state. This arm wasn't shrinking, but it has an initial velocity of v1.5 feet per second. So the velocity v1 vector, and this is v total, okay, has a component in the r hat and another component in the theta hat. Okay, in the theta hat, if you guys remember, r is always in the arm direction. This is r. And theta is perpendicular to r in the direction of increasing velocity. So theta is this way, right? So v1 is vr or v theta? The one that is given. So I said it's a v1, but this is not the whole velocity. It's a v you need to figure out. Like I gave you in the problem, I told you, is the crate is moving v1 0.8 feet per second in a straight path. Okay, so this is actually v theta. So I have 0.5 here, and it's positive because it's in the same direction of the motion, right? Okay, I told you that at this point, this arm is not moving, not decreasing or increasing in length. So VR is gonna be equal to 0. So V1 is equal to 0.5 as a magnitude. Because if you take the square root of 0 plus 0.5 squared, you're gonna get you 0.5 feet per second. Okay, so I got the quantity of V1. And what I'm asking for, what is the velocity vector r and theta of the motor at position 2? So I need to find out V2, which has component VR2 in the r hat direction plus V theta 2 in the theta hat direction. I need to find this. What I'm gonna use here, I'm gonna use the principle of angular momentum. So let's write here. Number one, what I'm gonna use, angular momentum. Okay, for angular momentum, we need to study this body because my equation is the r vector number 1 crossed by mv1 vector plus the integration from t1 to t2 m of dt is equal to r2 vector crossed by mv2 vector. That's the equation, okay? Right now, I have the velocity v1, I need v2, I have already r1 because I know how much is the r at the initial position and how much is the r at the final position, so I know r1 and r2. But what I don't know is the moment. So to get the moment, I need to find what is the forces acting on this body. Okay, let's put this crate something like this. This is our crate, 80 pound, and it's connected to an arm, maybe something like this. And this arm is connected here to a system at this point. Let's put all the forces on this crate. What forces on this crate? Like weight. Okay, the weight is going down because this is horizontal, right? So the weight is going down. What other forces? The force that I'm asking here. How much work does the arm do? So this arm is pulling this crate this way with a force Fr. Okay, so that this crate can decrease from, like the length of this arm can decrease from 2 feet to 1 feet. So this arm definitely has a force, Fr. And actually, if this crate is moving on a surface, like if there's a table and this crate actually is moving on a table, so definitely there might be some end force, but I don't have this right now. Okay, so if I want to find out the moment of these forces, so let's do this equation. I want to find out the moment. Here's the sum of the moment, MO about dt. How? I don't have time, so you will definitely doubt yourself. I don't have time. How am I going to solve it? Just hold on. MO is going to be 0. So let's find out how it's going to be 0. Let's find the moment of this force. We need to find the moment that is in this direction. Okay? That gives us a moment this direction. Alright, so I want to find the moment about this point. Okay? So this force passing to this point, does it going to have any moment? It's not going to have any moment.
No.
How about the moment of W about this part?
Yeah.
Gonna have a moment about this line?
Oh, no.
So you have a line like this right now. Okay, so here's the arm. It's something like this. We need to find the moment about this shaft, okay? And we have something like this. This arm is going this way. So the moment of this force, it's passing by this line, right? It's not gonna make, because it doesn't have any arm, right? The weight is going down. It doesn't make any moment because the line that I'm getting the moment about is parallel to the force. So it doesn't gonna have any moment. When you're gonna have moment is your force this way. So this is gonna, like if I have a force this way, this is when you are gonna have a moment. Like something like this, so this is gonna make a moment like this. That's why this is gonna rotate, right? So this is the only way. But the weight is not making any moment about this line. If you have two forces, if you have, force and you want to get the moment about a line parallel to the force, it's a 0. Okay? But if it's this way, just be careful about the direction. Because as we said, the moment is the cross product of the r vector and the v vector. So here F, and the one that you get the moment about, the r goes in the same direction. Theta is 0. Okay, so the weight and the force doesn't make any moment, so the moment is equal to 0. So when I will have a moment, you will have a moment if I told you that this crate has a force out of plane acting this way for a time 3 seconds. This force is going to make a moment, and we will have the arm of the moment. You multiply them, you put MO, and then you put from t equals 0 to t equals 2, and you find this value. But for this problem, we don't. Okay, so we will be left out with R1 multiplied by V1. You guys tell me, what is the value of R1? The position, the R. What do you guys know what is R? It's the position from the body to the point that I'm getting the moment about.
2 feet.
So
2. Is it positive or negative? It's always positive.
Oh, positive.
Because it's going this way. It's going to be 0 if it's on the other direction. So the R vector is 2. Alright, what is the direction of this 2? All the value of 2, where? Is it in theta hat or r hat? R hat definitely, because this is r. So it's all in the r hat direction. Multiply cross product by mv1. Actually, m is 80 bound, so I can put 80 over 32.2 multiplied by V1. I have V1 is 0.5 theta hat. Okay? This is equal to, so we are done with the first part. Let's get to the second one. What is the value of R2? R2, this is 1 feet, right? So it's gonna be 1 in the direction of R hat multiplied cross product by the mass, which is 80 over 32.2, multiplied by V2, which I don't know, but definitely V2, if V has two components, VR and V theta. VR doesn't matter, because if you have VR, like if I put the VR component, and it has a direction R hat, so multiply R bar hat, so it's gonna be 0. So it's not gonna, but you can put it, like you can say VR2 in the R hat direction plus V theta 2 in the theta hat direction, okay? So let's get this. I can divide by the mass, it's gonna be something like this. So you'll end up with 2R hat multiplied by 0.5 theta hat. I need to tell me, if I did this product, what is the magnitude and what is the direction? The magnitude is 2 multiplied by 0.5 is gonna be equal to 1, right? And what is the direction? If you multiply R hat by theta hat, Z, right? So if this is R and this is theta, and you multiply R by theta, we know actually they are both perpendicular to each other, so you will have in the k hat direction. So 1, so it doesn't have to be x and y. All what you have to do is it perpendicular or not? So this is R, this is theta, so R multiplied by theta is gonna give you a vector perpendicular on these two, like this. So, and we are gonna call it Z, all right? Okay, so it's gonna give you 1 in the k hat direction. So this is gonna be equal to, let's get the other one. 0. If you multiply R hat by R hat, it's gonna give you 0. If you multiply R hat by theta hat, it's gonna give you k hat. So we have another k hat here. And what is the value, the magnitude? So it's 1 multiplied by theta, v theta. So I will be having here v theta 2. So v theta 2 is equal to 1. Actually, v theta, we can call, I believe, radian per second. Well, okay, let's say radian per second. All right, so right now we have v theta. How about VR? We've got the component v theta. Actually, that's why we need to read the problem carefully. So it says that just after an arm begins pulling the crate from R1, 2 feet, to R2, 1 feet, with a constant radial velocity, VR equal 0.4. So 0.4, this arm is moving toward this direction with 0.4 all the way constantly. So when it gets to position 2, it's still constant. So VR2 is going to be equal to 0.4. So this will give us that V2 vector has an R direction of 0.4, and it's negative because the arm is going this way, and in the direction of R hat, plus 1 in the theta hat direction. So right now I get the V2. If you want to get the V2, the total value, you get the square root of 0.4 squared plus 1 squared. This will gonna give you 1.077 feet per second. All right, so we are done with what is the velocity at position 2. So let's get how much work does the arm did. So we will get back to the concept of work and energy. You guys remember the concept of work and energy? We have half mv1 squared plus mgh1 plus the work done by the non-conservative force from 1 to 2 is equal to half mv2 squared plus mgh2. Right now we don't have a potential energy if this arm is moving vertically, so we will have a potential energy. So mgh1 is 0, and mgh2 is 0. I have half mv1 squared, so half 80 over 32.2 multiplied by v1 squared. v1 is 0.5, and actually when we say v1, this is the total amount of velocity, radial, so you need to get not the vector component, you need to find the scalar component. And with a scalar, because the energy is a scalar quantity, not a vector quantity, so everything should be scalar. So I have 0.5 squared, plus the work that we are looking for, coming from the R, is going to be equal to half 80 over 32.2 multiplied by V2, which we just got, the scalar quantity 0.077 squared, and we can get the work. So this is going to be equal to 1.13 feet pound. This is the work. The easiest part is how long the arm take from 1 to 2, and that's very, very direct because it told you that this arm decreased from 2 feet to 1 foot. Okay? And you know what is the velocity that this arm is moving with. The velocity is 0.4 feet per second. So if you know the velocity and you know the distance, we know that the velocity is delta S over delta T. The difference in the distance and the difference in the time. If I told you I walked from here to this door and delta S is like 10 meters and I cut it in 3 seconds, so 10 over 3 seconds is gonna give you the velocity. But right now I know the velocity is equal to 0.4. And I know that delta S is 2 minus 1. You can put them in negative, like you can put in negative here if you want, but here you will have to put 1 minus 2. If you put this in positive, this should be 2 minus 1. Because the final position is 1 and the initial position is 2. And what I'm looking for is delta T. So we will find out that delta T is equal to 2.5 seconds. I believe this is the hardest part in the impulse and momentum because it includes lots of cross products. But once you pass this, we are done with the particle kinetics and kinematics. So there's no particle anymore. Does anybody have any questions so far on this part? Is it difficult? Right? Difficult, huh? But if you are, dynamics need to be systematic. You need to know what equations that you are gonna apply. You need to understand the problem first. Once you understand, you know, is it a working energy problem? Is it an impulse and momentum problem? Is it a Newton problem? Once you know this, you set the problem and you put the equation in front of you. Like you put this equation if it's linear momentum. You put this equation if it's angular momentum. Once you put the equation in front of you and you understand the problem, it's just substitution. You need to figure out what is the value of R, what is the value of V, what is the value of the moment, and you keep getting them one by one. Solving problems is gonna be make you like to know how to solve problems, which equation you should put. Dynamics, as I told you, it's hard. It has lots of math, lots of physics. So you need to get back to the basics, understand them, and then come back here. Understand the problem. How does the motion look like? Like when I sit here, top view. Yeah, top view is the arm is moving like this, so there is no potential energy. So the weight doesn't matter. If it's the arm is moving vertically, so here it's gonna matter when we write mgh1. Okay? So that's why you need to understand every part of the problem. Solving more problems is gonna help you to get better in this class. All right. So right now I have 30 minutes. I'm gonna make an introduction to structural dynamics. So all this is just to build some basics to help you as a structure engineer to understand the dynamics of the structure, because the structure has dynamics as well. So let's see if some of you want to be structure engineers. You need to focus on what I'm going to do next. All right, so structure dynamics. all what we have done till now is particle kinetics and particle dynamics, not rigid body. Right now we are gonna do structure dynamics. But let's say as a structural engineers, like if you are structural engineers, what we care about when we design structures, we care about two things, okay? Like let's say I'm a structural engineer, I'm gonna design this floor. What I'm care about that this floor, about two things. We call it serviceability and resistance, okay? We need to make sure that this floor, when we all sit on it, it doesn't fail, like it doesn't have a bending moment. This bending moment exceed the resistance of the concrete or the steel, and then the whole floor can fail, and it fails. Okay, we call this failure. You know what we call what else that we call failure? Let's say that I'm making like this on my floor, and you over there hear that this floor is moving or shaking. We call this serviceability. Yeah, it didn't fail, but it makes displacement in the floor that everyone feel and makes us uncomfortable. Okay, so that's why when we have a standards on the structures, it limits what we call the maximum deflection. All right, we designed this floor and we make sure that this floor with the amount of loads, live loads, our loads, the loads of the chairs and the desks, and the dead loads like the flooring and the whole body itself is not gonna fail. But even with that, when somebody walk on some floors, like if I have my neighbors walking over there, I can't hear them, I can't hear the whole thing's moving. We call this, we need to put limitation on the displacement on the floor. Like if you have, this is my floor, like this, and once you put all your loads on this floor is gonna make something like this. All the floors, even the floor that we hear, but this displacement is very, very small. Like it's something, it's relative to the length. Like if this is L, for example, they call that the delta maximum shouldn't exceed, for example, L over 6 or L over 24. 6 is like 24 or something. Okay, so there's a maximum based on the span of your structure. So that's two things that we need to care about, displacement and forces. But let's subtract what happens to the structures step by step. First, we have our structure, right? We put the loads. This is our loads, B. Let's say that this is loads B. What happened to this structure is gonna have deflection, delta. We call this delta. Once this delta happen in your structure, the structural member is gonna have a strain, right? Because there's displacement. Once this displacement happen, this, like all the particles, like if we take a cross section here, let's say that this is a beam, okay? And a 3D, something like this. If I take a cross section, it's gonna be something like this. It's gonna have a bending moment. It's gonna make like this. So this is what we call bending moment. So the section on the top is gonna be under, like let's say, this is my beam, and it's gonna make like this. So the section on the top is gonna have compression or tension? Compression. And down is gonna have tension, right? So the cross section is gonna have here compression, and it's gonna be something like this. This is compression. It's gonna be compressed until it comes to a neutral axis, and then you have some tension, right? So the delta is gonna make strains, and the strains is gonna create the stresses. Okay, so this is loads, deflections, strain, and stresses. That's the cycle of the structural analysis. All right? Okay, so so that's actually our job, is to get the displacement that happens in the structure. We need to find what is this delta. Is it beyond the maximum or below the maximum? But with the structural dynamics, the thing is, when I give an example about this floor, all our loads right now are static loads. Even that we are moving, like with the way that we designed this floor, we calculate all our weights. Let's say everyone is average is 80 kilograms. When we got all the weights, let's say 100 multiplied by 60, so 600 or 1,000 kilograms, like 1 ton. We distribute the 1 ton by the floor area, and every 1 meter by 1 meter is getting 200 kilogram or 100 kilogram per square meter. This is how we distributed our live load on this floor. Same thing. So we consider live loads, but this live load is still a static. The own weight of the structure is a static. Everything is a static. When the loads start to be dynamic, what kind of loads that can be dynamic? So that we can study the dynamics of structures. Like if I have a structure like this, building, this is the ground. When this structure starts to have some dynamic movement, when the load is dynamic, like what? Like wind and earthquake, explosions, and that's what we are looking for here. Earthquake is something, is force that is not constant. It's force that keep it changing. Like somehow your structure is moving like this, and then it's shaking hard, and then it's shaking down, and then it die out, like something like this. This is the ground, and this is the time, and this is the force of the earthquake. It's something like very, very small with time, and then keep getting increasing, and then it have a very high shock, and then it die out, and maybe there's some aftershocks, and then it die out. So this is the main shock, and this is the aftershock. Some earthquake doesn't come with aftershocks. Okay? So this is time with the acceleration, and we call this the ground acceleration. And if you have the ground acceleration, you can get the force of the earthquake. You multiply mass by the ground acceleration, you can get how much force that this building is absorbing. And actually, every building, like let's say Miami got hit with earthquake, and this is really happening. But let's talk about Los Angeles, LA, got hit with an earthquake. Every building has a different mass. However, the earthquake is the same, have the same gravity, but every building is gonna absorb different force from this earthquake, depending on the mass. If your mass is big, you're gonna absorb more force. If your mass is small, you're gonna absorb less forces. Okay, so this is, we call it AG, or the earthquake acceleration. And it's all, this is the difference between the wind and seismic loads. Winds come from the top, earthquake come from the ground. Okay, so it shakes the ground, and then the ground shakes the building. But wind shakes the building, and the building shakes the foundation from the ground. This is the difference. But the thing is, solving an earthquake problem for a building like this is very, very hard. Why? Because as I told you, we engineers, we are interested at delta, okay? But this building has lots of degrees of freedom. Like, I wanna know the delta here, I wanna know the delta here, the delta here, the delta at all the structure points. The structure has multi-degree of freedom. Like, this point is moving different from this point, is moving different from this point, and it's a 3D, so it's a very, very difficult problem. Engineers see two things. We need to make simplicity. We need to make this structure as simple so that we can solve it, and condense it in a way that can give us accurate solutions. In the same way, it is possible. Like for example, sometimes we do simplicity, but it messes up with the accuracy. We need to make it simple and at the same time accurate. So how can we do this? So to do this, I want to do something first. Let's say we have a bar. This bar is something like this. And another bar that is much bigger than this bar, something like this, very, very big. And they are all attached to a wall, like this. And there is something here that a rigid body, and we applied a force like this, F, on these two. What is gonna happen? Both of them are gonna take this force in, right? But if this is a rigid body, and this force is pulling this way, at some point, this bar is gonna come here. So it's gonna have a delta, right? Okay? So what is special about this problem? We simplify this problem. This one as a spring, and this one as a spring. This one has a K1, we call this axial stiffness, and this one has a K2. And both of them are attached to a rigid body, and we have a force F or B, let's say E, this way, okay? So the special about this, we call this springs in parallel. So those two are in parallel. If the springs are in parallel, so delta 1, like delta for this spring number 1, is equal to delta 2 is equal to delta. Like both springs are gonna move, this is delta 1, and this is delta 2. And delta 2 is equal to delta 1 is equal to the delta of the system, okay? But the spring number 1 is gonna absorb a force B1 is different from the spring here B2, but B is equal to B1 plus B2, the final B, okay? Who is gonna take more force? The one that has more stiffness, right? Okay, The one with less stiffness is gonna take less force because both has the same delta, and we know that the force P is equal to K multiplied by delta, right? Both of them has delta 1 and delta 2, so definitely the one with the higher stiffness is gonna have a higher force. Alright, so right now I know that delta 1 equal delta 2 equal to delta, and I know that B is equal to B1 plus B2, so I know that B is equal to K multiplied by delta, so I can say that the K equivalent of the two springs multiplied by the delta of the spring of the equivalent is equal to B1 K1, which is K1 delta 1 plus K2 delta 2. I can write it this way, but actually we can divide by, like we know that delta 1 and delta 2 and delta, all of them are equal to each other, so what can I do? I can divide by delta, right? Because this is equal to this is equal to this. So basically, if you have two springs in barrel, you can sum the stiffness K equivalent is equal to K1 plus K2. That's a very, very good simplification that we can do. So this if we have system in barrel. What if the springs are in series? The springs are in series, so if you have a bar like this, and it's attached to a bigger bar, like this, and my force is this way, B. Okay? I can simplify this by a spring and another spring. And spring 1 has K1, and this is K2. What happens here, if you have two bars, this is a bar and this is a bar, attached to each other. One has K100 and this one has 50. And you push them with force B. Both of them has the same force. Right? This is force B, and actually the reaction is B, so the force B is constant in both of them. So this one is gonna have B, and this one is gonna have B. But what happens is, this one is gonna have delta 1, maybe something like this, and this one is gonna have very, very small delta 2, because it has bigger stiffness. Okay? And the final displacement of the whole system is gonna be final delta, which is delta 1 plus delta 2. The delta that happens here plus the delta that happens here. This is what is gonna happen. So what we have here, we have that B is equal to B1 equal to B2, right? And I have that delta is equal to delta 1 plus delta 2. I can substitute here by delta. Delta is equal to the force B over the K equivalent of the system. This one has the force B1 over K1 plus B2 over K2. I know that B is equal to B1 plus B2, so I can divide by B. So all this is going to be gone. So I will have 1 over K equivalent equal to 1 over K1 plus 1 over K2. And if I want to get the K equivalent, so this is going to be equal to K1, K2 over K1 plus K2. If you have a system in series, okay? All right, why I'm saying this? Because the structure has the same thing. Let's say that this structure got hit by an earthquake or got hit by a wind. What is gonna happen to this structure? When we look at the structure as a structure engineers, we don't look at the chairs, at the flooring, at the ceiling. We imagine this structure as foundation, columns, beams, and slabs. That's the structural elements that we care about. Other than that, it doesn't make like any visually change to us. That's how we look to the structure, because this is the things that we design as a structure engineers. When I get something from the architecture, I need to design the superstructure first, design the columns, design the beams, design the slabs. Okay? Once I do this, I found the loads on the foundation and then design the foundation. Either it's gonna be isolated, piles, raft, foundation, whatever it is. But here, looking at this structure, I'm looking as a columns, beams, and slabs. That's how the structure looked to me. And if this structure got hit by an earthquake, what is gonna happen? All the slabs is gonna move like this. This is the big masses. Like this is the masses is the one that I want to resist. This masses doesn't move. I want this mass to stay still. What makes this mass still is the stiffness of the column. If this column is very, very stiff, it doesn't let the mass to move like this. I wanted my slab doesn't shake like this, so it needs a very, very stiff column. So when an earthquake happens, a very strong one, so the displacement is going to be something like this. Okay, so the slab on the top story is going to have a very high displacement. Why? Because it's going to add up. This one is going to move delta, and this one is going to move delta, this delta plus another delta, and this one is going to move this delta plus another delta, so every one as you go up is going to have much higher displacement, okay? But there's something that we can relate to what we did here. Look at the delta of this column and this column and this column and this column and this column. All these columns have the same delta. Why? Because they are attached to a very, very rigid slab. Like let's say the slab is very rigid. If the slab is moving this way, it's gonna take all the columns with it. Not gonna leave another column, like not gonna take 10 and leave 10. So if we are all gonna move this way or this way, we're not gonna leave each other. So both of them have the same delta. So let's say here, delta 1, delta 2, going up until delta n. All right, so all of them has the same delta. What this means is that a barrel or a series system. Just think. Barrel. Why? Because the two springs here has the same delta. I have a rigid body, take all of them, delta 1 and delta 2, didn't leave. If I have another spring here, so it's gonna have the same delta. So all these columns are in barrel. So if this column has a stiffness K1, K2, up to Kn, so if I want to get the whole stiffness of the story, it's gonna be the sum of the all K's in the story.
So does that mean, since also the force is going to be different in each beam, the more beams we add, the more the force gets distributed?
Well, but the thing is, the beams add more stiffness to the slab, so it's gonna make the slab more rigid. Because the slab is not perfectly rigid. Because as you increase the thickness of the slab, it's gonna be more rigid. That's why we say that the slab, is it rigid or flexible diaphragm? So when we design structures, if your slab has lots of holes, like you have an elevator and you need to make a hole, you have a stair and you need to make a hole in the slab, that decrease the stiffness of the slab, make it less rigid. That's why the standards say, based on the number of voids that you have in your slab and the thickness of your slab, you can consider your slab as a rigid or as a flexible diaphragm, okay? So adding more beams is gonna make your slab more rigid. All right, okay, so story number 1 is gonna have sum of all the K's here. Same thing with the story number 2, K2, K3, up to sum of Kn. All right, so we are done with one part. Let's go to the second part. All right, so what I did right now, I lump sum all the stiffnesses, all the columns, like I have a column here and a column here and a column there. I sum all the stiffness of these columns in one column, one big column, like something like this. My building starts to be sum of K, one column and the mass of the slab, one column the mass of the slab, K2, K3, up to sum of Kn. All right? Okay, so let's give it another look. The delta, this is delta n, delta 1, delta 2. Say that the earthquake came this way, F quake. Right? What's going on here? Look at here. You have here delta 1, and this delta is this delta plus this delta. So it adds up. So the delta on the top is the sum of all the displacement from the other story. Is these columns are in series or in pairs? Series, like this one, right? You have delta 1 here and delta 2. If you add them up, you get the total delta. So these columns is in series. So if you want to convert, this is going to be something, one mass, and these masses are in series, and one column that has one big stiffness, sum of K equivalent. So what we did right now, we condense it, a very, very complex system, like a building that has hundreds of thousands of degrees of freedom. Because right now we are not talking about degrees of freedom in the X direction, this is 3D. So each point in this building, each corner, has a degree of freedom in the X, a degree of freedom in the Y, degree of freedom in the Z, and rotation about X, rotation about Y, rotation about Z, multiple degrees of freedom. And each story has 100 points. And this 100 points, each one has 6 degrees of freedom, and we have multiple stories, so it's a very, very complex system. So we converted this system to what is called multi-degree of freedom system, MDOF, multi-degree of freedom system. And then we convert this system to a single degree of freedom system. Right now I can solve this one. That's a very, very easy one, and I can solve it manually by my hand, okay? All right, so we are done with the stiffnesses. So when an earthquake hit a structure, and this structure is gonna resist this earthquake with the stiffnesses of the columns. So the second thing that I need to think about, there's something that's called damping. What is damping? When an earthquake hit a structure, is this a structure is gonna move forever?
No.
At some point it's gonna stay still. So what makes this a structure still? 2 things are resisting, or 3 things. The mass, the stiffness, and there is a third component, is called damping. What is damping? So when you have a joint, like a column and the beam are opening and closing, so there is a cracks. Opening and closing the cracks, adding a damping or making the force to die out. So that's why we add these components to the, I'm not gonna talk more about it. Sometimes people solve systems, they call, I'm gonna neglect the damping. And right now, so the verse line that I have here, this we call stiffness, K, and this we call C, damping. Sometimes people neglect the damping and they call we are gonna solve single degree of freedom undampened, and sometimes people consider the damping that can't happen. Sometimes we add damping to the structure, like we add what is called dampers. Like they put an hydraulic arm, so when an earthquake hit, this arm keep opening and closing to add more damping to the structure, so the damping is gonna increase. Some people, I'm not sure if you guys heard about Taipei 101 building. It's in Taiwan, I believe. Yeah, they have like a water tank, like a bowl that has a water. So when an earthquake hit this way, the water goes the other way. So that's called add more damping to the structure. So C is more damping to the structure. So this is a very, very important component, okay? And actually when we write K, this K is not axial because there's, what I did here, this is an axial stiffness. Like your column is in the axial direction, but what we are resisting here is shear stiffness. So if an earthquake is hitting this way, so the spring is, it should be something like this. Look, if I cut here, so I should make the spring something like this, because it's a shear stiffness. Same way, if I did here, it should be something like this. So this is K, and this is C. All right, so right now I have multi-degree of freedom systems 3D, multi-degree of freedom 2D, and single degree of freedom T. That's what we are gonna do here in this course next time, is how to solve a single degree of freedom structure. But there's a thing. Solving this means that you solve the entire structure, not solving 1 degree of freedom, because once you get the delta, like this, let's say that this got hit with an earthquake F, and you were able to get how much displacement here that this mass is gonna do. This delta actually is this delta. So you got the delta for your entire structure. Solving this one, actually, when I take my dynamic class back like 10 years ago or something, solve it, maybe we can solve it 3 degree of freedom. Because it's gonna be a matrix 3 by 3. It can be easy. But if the degrees of freedom come more like 10, you need a laptop to do it for you. It's gonna be very hard. That's why we use softwares like SAP 2000 and SAP. When we solve building, it's all a multi-degree of freedom system when we do this. All right, so let's take, let's see very quick, build the equation of this one. So right now, I told you that this is the mass of the building, and actually this is M equivalent of the entire building, and then you have a stiffness like this, and and then you have C damping something like this, right? So what I want to do, I want to get the equation of motion of this building. How? So if we imagine that this building is like a mass, something like this, M, and it's attached to a spring this way, and also we call this dashpot. Dashpot, which means a damper, something like this. And after you apply an earthquake force, let's say, because the earthquake force is a force that varies over time, let's say Ft, this mass is gonna move this way, it's gonna have Ma. We're gonna apply the Newton's second law. So the Newton's second law is something, the sum of the forces is equal to the mass multiplied the acceleration. All of them are in the x direction. Okay, so what is the forces that I have? I have a stiffness. The stiffness force, as we agreed before, is K multiplied by delta, right? Or by U, like let's say that this mass moved U, so I have K multiplied by U. C is the same like K. We can multiply C by U, but actually we're gonna make it U dot, because the damping is in a relationship with the velocity, and this is constant. So this constant multiplied by the velocity, this constant multiplied by the displacement. Okay, so you have K multiplied by U. This is gonna give you stiffness force. C multiplied by velocity is gonna give you damping force, right? So let's find out the total force that is applying on this structure. First, and actually MA is, let's put M, and I'm gonna write A as a U dot, double dot, okay? Because A is the d squared u dt squared, so it's the second time derivative, so I'm gonna make it u double dot. Okay, so let's put all the fx's, and I'm gonna say that this is my positive x direction. So I have ft, alright, minus k multiplied by u, because this is the force, and minus c u dot, because this has a force, another force here, is equal to m u double dot, something like this. Right, so what I'm gonna do, I'm gonna send these two in the other direction, so I will end up with, let's write it here, m u double dot, and this is gonna be positive, both of them, so I'm gonna write c u dot plus k u is equal to f t, and this is very, very important equation in the world of structural dynamics. Very, very important one. You're gonna do your BE exam after many years. This is very, very important when we solve the structure. All right, so this equation has a mass, has damping, has a stiffness, and has an earthquake force. And this we call differential equation. Have you guys heard about differential equation? So what is the degree of this equation? Second degree. Why? Because I have u double dot. So solving this differential equation, what does it mean by solving this differential equation? Is to find u. If I found u, that means that I found the displacement that this structure is gonna make, right? So solving this, that's what we are gonna do next time after 3 weeks from now, is to solve this equation. But what is complex about this equation that makes it very, very complex? The ft is not constant, it's a variable over time. And it doesn't have a function that you can build. Look at this function. Where did we do the earthquake? Oh, midweek. Okay. So where is it? So it's something like this, and the force is keeping changing, right? So we need to divide this into small segments. Every segment is constant, and we call this the Duhamel integral, so that we can solve this equation. We're not gonna do this, but you should know that, because this force is not a function, it's something like t, and this is the force, and it's something like this. So we need to solve this equation to get u, and once we get u, we solve the entire structure. So I'm gonna stop now, 3 weeks for spring break, 2 weeks of fluid dynamics. We are gonna revisit this concept, but I thought that I might make an introduction so that you guys be prepared. All right, see you guys after